Critical frequency design develops state-of-the-art communications, sensing, and processing technologies utilizing open systems and a digital engineering approach. We've been selected for 7 Phase 1 SBIRs with 100% conversion to Phase 2 and awarded 1 Phase 3 SBIR. Our technologies include free space optics, advanced photonic and fiber optic components, and model-based systems engineering. We're subject matter experts in photonics, MBSE, digital engineering with significant experience in Cat 1 programs. We've delivered over 100 systems to Tier 1 defense contractors. We're AS9100 certified. We have a secret facility clearance and a 20,000 square foot facility in Melbourne, Florida in support of microelectronics and subsystem development and manufacturing. Since June of 2018, the OSD's digital engineering strategy has encouraged digital models for military systems. Yet most defense systems are delivered without this digital resource. In 2023, the DoD formalized this strategy with an instruction, the 5097, making digital engineering a requirement. Additionally, the DoD is requiring systems to use a modular approach. MOSA, the Modular Open Systems Approach, is the DoD preferred method for implementing systems and is also required by law. One of the published standards for meeting MOSA is SOSA, the Sensor Open Systems Architecture. SOSA establishes rules, guidelines, and interfaces for developing C5ISR systems. The complexity of modern weapons systems development is managed by requiring both a modular architecture and digital engineering approach. Our sponsor, NavAir, is at the forefront of the adoption of both of these technologies. Furthermore, the integration of avionics systems is increasingly relying on fiber optic communications to increase information throughput and reduce aircraft weight. To facilitate these initiatives, NOC-AD has tasked CFD to develop a SOSA Open VPX library for use with digital twin MBSE models, and then using this library to develop an optical transceiver circuit card assembly. In Phase 1 and the Phase 1 option, CFD developed a SOSA Open VPX library. This library included SOSA interfaces for plug-in modules and backplanes to the pin and signal level, and the components and modules defined by SOSA. The rules, observations, permissions, etc. defined by SOSA were captured as extended requirements. Selected 6U and 3U module profiles with RF and optical interfaces were created. We then modeled and performed a simulation of digital and analog optical links. In Phase 2, the SOSA library was used to create a 100 gigabit optical transceiver CCA. CFD will demonstrate the digital thread handoff from systems model to circuit design and then to breadboard creation. For the digital engineering strategy to succeed, an ecosystem of libraries and stable interfaces is required. CFD's SOSA library facilitates both of these requirements. Standards such as SOSA and OpenVPX can be distributed digitally as SysML models rather than as documents, and this project demonstrates that improvement in distribution. System-to-system integration at the MBSE level requires a common interfaces shared by both models. This is met by the common OpenVPX library. The use of a standard government-managed library ensures digital twin models for all new systems are developed to the same level of accuracy and depth. The 100 gigabit optical transceiver development provides a real example of this use, a real example of digital thread development, and a high-speed optical link for future avionics development. Phase 2 was intended to have a shorter base period and a longer option for hardware development. The current status is that we're nearing the end of Phase 2 with a circuit design for an OpenVPX 3U carrier board and a mezzanine card transceiver. The Phase 2 option is expected to develop this mezzanine card to the breadboard level. The ever-increasing complexity of systems and capabilities, major systems developments have increased in time and cost. Digital engineering has an opportunity to make drastic changes to this trend by conducting mission use case simultaneous with use cases, thereby validating requirements much earlier. Although model-based systems engineering is being required, the adoption can still be challenging and the value is misunderstood in an era of programmatic budget constraints. CFD has worked to showcase the value of model-based systems engineering, developing digital twin models and reusable libraries, and by conducting use case demonstrations of key functionality to tie mission use cases to system behavior, and then tying the system behavior to the allocated requirements. These demonstrations have been made to the Navy Program Office and OEMs. With the maturity of digital engineering, CFD is taking advantage of Navy-sponsored transition activities such as STP, and has demonstrated the model to other DoD organizations. And will work with other defense contractors to identify opportunities to utilize the current model and expand it for next-generation architectures. CFD plans to maximize the sharing of our digital twin models. Our efforts will include developing an online store that organizes our models into key categories. As indicated on this chart, our store will support open systems standards, reusable common components, cybersecurity libraries, and SCA libraries. We'd also allow other vendors to host on our portal through commission or markup business models. We'll provide a plan for OPSEC for sharing our site in accordance with our customers' security requirements. Our marketing approach is indicated on the left side of the chart using an attract, engage, delight strategy. We would focus on content to generate leads for cultivation within the sales and BD funnel. Thank you. For more information about critical frequency design's products and capabilities, please contact Jonathan Warren at the email shown below.